We will now see another technique that can be used to obtain information about the 3D structure of proteins. It's nuclear magnetic resonance. So here the main difference between NMR, so nuclear magnetic resonance, and X-ray crystallography is that in the case of NMR, you will study the biomolecule in solution. So in this case, it's not necessary to first obtain a crystal for the protein. This is really an advantage because the molecule is directly in solution. But you have also some disadvantages in the case of NMR, in the sense that it's possible in general to study only small size proteins, typically 400, 500 amino acids. There exist techniques that can be used to study larger molecules, larger complexes, but these techniques are quite difficult to proceed. So now on what is based on NMR. In fact, NMR is a spectroscopic technique. We will see a little bit later in this chapter other types of spectroscopic techniques, like infrared spectroscopy, for instance. In general, and we will discuss that a little bit in more details later, in classical optical spectroscopy, you will study the absorption or the emission of an electromagnetic wave. And you will study the emission or the absorption of this electromagnetic wave by your sample, by the molecules that are present in the sample. We will see that this emission and or absorption correspond to different transitions between energy levels. In this case, the matter radiation interaction is through the electric component of the electromagnetic wave. In NMR, in fact, we will see that it's a little bit different. So first, you will have to induce here an energy difference between the different levels. And to do that, you will place your sample in a magnetic field. So that's the first difference here. A second difference between classical optical spectroscopy and NMR is that the matter radiation interaction is through the magnetic component of the electromagnetic wave. And as a result, this means that you will involve here smaller energies compared to the interaction through the electric component. And finally, what we will study here, it's mainly the magnetization of the sample instead of the transition between the different energy levels. So that's the main differences between NMR and more classical optical spectroscopy. So now we will see a little bit some theoretical aspects of NMR to understand the logic of the technique. So first, in the case of nuclear magnetic resonance, you need that the components, the sample, the molecule present a magnetic moment and an angular moment. So the magnetic moment is a vector. That's the reason why you have here the small arrow above the mu. So mu is the symbol for the magnetic moment, the symbol that I will use here in the course. And the angular moment, J, it's here, it's also a vector. First, all the nuclei of the atoms in a molecule do not present these characteristics. We will discuss about that a little bit later here in the video. You have here a first equation that makes a relationship between the magnetic moment mu and the angular moment J. The equation is here, and you see that mu is equal to gamma times J, and gamma is the gyromagnetic ratio. It will depend, it's a quantity that will depend on the nucleus, and it's related to its sensitivity to the magnetic field. Then you have a second equation here. You have the equation that says that J is equal to a constant h bar. H bar it's the Planck constant that is divided by 2p times I, and I is the spin of the nucleus. What is important here is that you see that to have here a magnetic moment that is different from zero, you need a value of the spin that is also different from zero. And what is important here is to understand that to do nuclear magnetic resonance, you absolutely need a mu, a magnetic moment that is different from zero. So you need that in your sample you have atoms that present nuclei with a spin that is different from zero. If the spin I is equal to zero, then the magnetic moment is also equal to zero, and it's not possible to have an interaction between this nucleus and the magnetic field, and so it's not possible to do NMR with a spin that is equal to zero. Now, if I have a look to different types of atoms that you have in proteins, you have, of course, carbon atoms. For carbons, you have different possible isotopes. The most abundant isotope is carbon-12. Well, carbon-12 presents a nucleus that have a spin that is equal to zero. So, in this case, the magnetic moment of carbon-12 is equal to zero. So, you cannot use carbon-12 to do NMR. You have exactly the same for oxygen-16. Here again, the spin is equal to zero, so no magnetic moment, and so it's not possible to do NMR with the nucleus of oxygen-16. On the other hand, you have other atoms that present a spin that is different from zero. For instance, you have the isotope 1 of hydrogen that has a spin that is equal to 1/2. And so here the spin is different from zero. So you have here an angular moment that is different from zero, and you have a magnetic moment that is different from zero. And so it's possible to do nuclear magnetic resonance by using the nucleus of hydrogen-1. And you have the same for carbon-13, another isotope for carbon, nitrogen-15, phosphorus-31. Here, the fact that hydrogen-1 presents a spin that is different from 0, and the fact that hydrogen 1 has thus a magnetic moment different from 0, it's a very good news, because in protein you have a lot of hydrogen atoms, and the most abundant isotope for hydrogen is hydrogen 1. So that means that in proteins you have a lot of hydrogen 1 atoms, and so it's possible to study this atom, this hydrogen atom, with nuclear magnetic resonance. And so you can use nuclear magnetic resonance applied to hydrogen 1 to study the structure of proteins. So, what happens now when you will place this nucleus that presents a magnetic moment that is different from 0 in a magnetic field? So here we will place this nucleus in a magnetic field that I will call B0, and we will see that there will be an interaction between the magnetic moment of the nucleus and the magnetic field. You have here two vectors. Here you have a scalar product, and minus the scalar product between the magnetic moment and the magnetic field is equal to the energy. Here I will just make a note, and we will discuss about this note again a little bit later in this video about NMR. In fact, you have to keep in mind that you have one nucleus, but around this nucleus you have, of course, electrons. And electrons are also charged particles. And here you will have an effect that is a shielding of the nucleus, of the magnetic moment of the nucleus, by the presence of the atom's electrons. So here, the magnetic field that is felt by the nucleus is in fact partially shielded by the electrons that are around the nucleus. So in fact, the nucleus will not really feel the B0 magnetic field, but the nucleus will feel a magnetic field that is slightly attenuated compared to B0. And that's what you have here in the equation. You see that the magnetic field that is felt by the nucleus, B, it's in fact B0, so the magnetic field that you imposed, times 1 minus sigma, and sigma represents the degree of shielding, and here again it's dependent on the nucleus, and it's dependent on the number of electrons that you have around the nucleus. And as I said, we will discuss that a little bit later. Then, what can we say about which kind of additional information can I give about the system here? In fact, what we will do is to place the B0 magnetic field along the z-axis. And this will simplify the different calculations here. If I orient the B0 magnetic field along the z-axis, you will have only the z component of the vector that will be different from 0. And so you will simplify the calculations here in the sense that the x and y component are equal to 0. And so when you compute the scalar product between the two vectors here, you will compute only the you will have only the component along the z-axis that will be different from 0. And so when you do the scalar product, you will see that finally the energy is just equal to minus the z component of the magnetic moment times the z component of the magnetic field that is felt by the nucleus. And so here you have just two scalars, you have no more two vectors. And if I use the equation that we have seen in the previous slide, finally you will see that the energy is equal to minus gamma, so gamma, it's here the gyromagnetic ratio, times the Planck constant divided by 2p, times the z component of the spin and the z component of the magnetic field. So you see that here the energy level is dependent on the intensity of the magnetic field in which you placed the nucleus. And keep in mind that Bz is equal to 1 minus sigma times B0Z. So B0 is the magnetic field that you imposed to the sample. Okay, then we have to keep in mind that in quantum mechanics, the allowed values for Iz, I will call this allowed value Ms, they are quantified and they vary between I and minus I. Here we are studying the case of hydrogen 1 atom. I said in a previous slide that in the case of hydrogen 1 atoms, the value of I is equal to 1/2. And so there are two possible values for Ms. It's only 1/2 and minus 1/2 if you respect this equation. And so if I take the equation that we have seen just in the previous slide, you will see that you have thus only two energetic levels for hydrogen 1 in a magnetic field. The first energy level is plus 1/2 gamma h bar Bz, and the second energy level is equal to minus 1/2 gamma h bar Bz. So that means that without a magnetic field, so if Bz or B0 is equal to 0, then you have you don't have these two energetic levels. There is no energy difference between the states, and here you have the different magnetic moments that are completely oriented randomly in the system. When you switch on the magnetic field, B0, then you will observe two energy levels. So with a magnetic field, the nuclei with a magnetic moment will orient. There will be two energetic states. The first one is E1, the second one is E2. And so here you have two possible energy levels. And so you have two possibilities for the magnetic moment. So that's only the case in the presence of an external magnetic field. Okay? And so you have a part in your sample, you have a lot of nucleus, and all these nucleus present a magnetic moment, and you have part of the nucleus that are oriented in the same sense of the magnetic field, and another part of the magnetic moment that are oriented opposite, in the same direction, but in the opposite sense of the magnetic field, external magnetic field. What is the population in these two states? We will discuss that in the next slide. So what is the ratio between the population of the magnetic moment in one energy level and the population of the magnetic moment in the other energy level? We will see that in the next slides. Okay, so here we have seen that with the external magnetic field, you have the two energy levels that are present here. Without an external magnetic field, you have no difference between the energy levels. So if I compute the energy difference between the two states, the energy difference is the difference between E1 and E2. And if you make this difference, you see that the delta E, so the energy difference between the two states here, the delta E is thus equal to gamma h bar Bz. And you can also show that it's also equal to h bar omega s, and omega s, it's a frequency. So if you analyze the dimension of omega s, you will see that it has the dimension of a frequency, and omega s is called the Larmor frequency. And so we have also the fact that omega s is equal to gamma Bz. So omega s depends on the intensity of the external magnetic field. Omega s, as I said, it's the Larmor frequency, and in fact, you can show that it corresponds to the frequency of precession around the z-axis of the magnetic moment. So if I show you the previous slide, so here, in fact, you have different magnetic moment here and here, and in the presence of this magnetic field, of this external magnetic field, you have in fact a precession of these different magnetic moments around the z-axis. But what is important to keep in mind is that there is no coherence in the precession of these different magnetic moments. So it's a little bit random for each magnetic moment. Okay? So here we have seen that you have a precession, and this Larmor frequency is also a resonance frequency, and so it depends on the intensity of the magnetic field. So for instance, for a magnetic field of 18.7 Tesla, the resonance frequency of a proton is equal to 800 megahertz. And just keep in mind that Bz here is the magnetic field at the nucleus. It's not the external magnetic field that you switch on, and you have the equation that involves sigma, and that makes a relationship between B and Bz and B0 Z. So here, what is important is the notion of this Larmor frequency, a first thing, and the second thing is that the energy difference between the two levels depends on the intensity of the magnetic field, and that the frequency of the Larmor frequency, depends on Bz, but also on gamma. Gamma, it's a constant for the different types of nucleus. Then, what is the ratio? We have seen that there are two energy levels. Now the question is, what is the ratio between the population of the two levels? We have here an equation that is called the Boltzmann equation. In fact, we will use a lot this Boltzmann equation in this course. We will use this Boltzmann equation also later, for instance, in the energy function chapter. This Boltzmann equation can be used to compute the relative population of different energy levels. And if we have a look at this Boltzmann equation, we can see that the number of nucleus in the first energy level divided by the number of nucleus in the second energy level is equal to the exponential of minus the energy difference between the two levels divided by kT. And keep in mind that we have just seen in the previous slide that this energy difference is dependent on the intensity of the magnetic field. So here we have seen in this slide that this energy difference is dependent on the intensity of the external magnetic field. And so you will see that the ratio here between the population of the two energy levels, so you have part of the nucleus that will adopt one energy level and other nucleus in your sample will adopt the second energy level, and the ratio between these two populations is dependent on the energy difference and thus dependent on the intensity of the external magnetic field. So here you have an example. So you will take the example of hydrogen 1. Here you have different intensities of magnetic fields. You have the corresponding Larmor frequency for these different magnetic fields, And here you have the energy difference in joule per mole. And here you have the ratio that is computed with the Boltzmann equation. And so here you see that to have a difference in the population in the two energy levels, you have to work with very strong magnetic fields. So you see that even with a magnetic field of 21 Tesla, you see that the ratio is very close to 1. So that means that you have a difference in the population between the two states that is very, very, very small. And why is it important to have an energy a difference in this population? It's because a little bit later we will study the magnetization, and the magnetization is in fact the resultant of the sum of the different magnetic moments in the two states. So if you have a ratio of 1, that means that you have exactly the same number of nucleus that present a magnetic moment in one sense, and you have exactly the same number of the nucleus that present a magnetic moment in the opposite sense. And so when you make the resultant between the two, you have a resultant that is equal to 0. So you need a difference in the population in the two states to observe something later in NMR. Well, I say here that 21 Tesla, it's a very strong magnetic field. Just to have an idea, when you use classical little magnet on a fridge, for instance, you see that sometimes you have magnet that you put on your fridge. What is the magnetic field that is generated by these small magnets? In fact, these magnetic fields are very weak. It's about 0.1 Tesla, maybe 1 Tesla, but clearly not larger. The Earth has also a magnetic field. The magnetic field of the Earth, it's about 10 power minus 5 Tesla. So you see that when you have magnetic field of 21 Tesla, it's a very strong magnetic field. And to obtain such an intensity for the magnetic field, you have to work with supraconductor materials. You have to cool these magnets, and in general you have to use liquid helium to cool these magnets. Just keep in mind that liquid helium is about minus 270 degrees, so it's quite difficult to obtain such an intensity for the magnetic field. So we have seen that there are different energy levels, and finally what we will see is that the fact that you have a difference between the energy of the two levels, the fact that you have a different population in the two levels, you will finally observe a macroscopic magnetization. And this macroscopic magnetization here, M0, it's the sum over all the individual magnetic moment of the different atoms. And so here we have seen that if you have exactly the same number of magnetic moments that are oriented in the same sense as the magnetic field, and the number of magnetic moments that are oriented in the opposite sense, then the sum will be equal to 0. We have no magnetization. Thanks to the fact that you have a small difference here in the two populations, so here you see that you have a ratio between the two that is different from 0. Thanks to that, you have a macroscopic magnetization that will be different to 0. And this macroscopic magnetization is oriented along the magnetic field Z in our convention, and the X and Y component of this magnetization will be equal to 0. So here, that's the first part about NMR. In a second video, we will see now how to use that to obtain information, to have structural information about protein. Because here, up to now, you have just a magnetization, but no more information.